Okay, so let's start. Welcome back to the last talk of today. And our speaker is Takato Yoshimura from the University of Oxford. And we'll talk about hydrodynamic fluctuations in integrable man-body systems. Let's welcome.
Thank you very much for coming today. I know that this is not the kind of fashionable things to talk about in this conference, but still, I'm glad that you chose to come to my talk. And also, I'm of course very grateful for this whole program. I mean, the International Congress of Basic Science for choosing our work to award this very nice prize. So here's what I want to talk about today. And I realized that I didn't probably have much time to talk about hydrodynamic fluctuations, but I will certainly talk about hydrodynamics for integrable systems. This is something I did almost like 10 years ago in this work. It's done in collaboration with these two people, Elijah Castor-Alvarado at City University of London and Benjamin Doyon at King's College, London. Right. And also I was a bit worried about, this risk that Bruno's talk in the morning might have a lot of overlap with what I'm going to tell you. But actually, I think our talks are going to be very nicely complementing each other. So hopefully you will enjoy my talk, even if you have heard this Bruno's talk earlier today. All right. So let me get started. So I thought, before jumping into the main topic, it would be nice to clarify what kind of systems I'm interested in this talk. So I am interested in the dynamics of quantum many-body systems, in particular quantum many-body integrable systems. So here I just put one such an example of integrable systems. So this is just written in the form of Lagrangian, just to well, it could be written in terms of Hamiltonian, but this is sort of looking nicer. Anyway, this is for example, the Lagrangian of this sine-Grondel model. So this is the first term is of course the kinetic term, whereas the second term is telling you how, in what way the system is interacting in the system. And because of the presence of the second term, this is a non-interacting model, but still, as it turns out, this model has a very nice structure called integrability. And what do I mean by that exactly? So the notion of quantum integrability is actually not a very full settled kind of concept, at least to my knowledge. And there are many kind of working definitions of quantum integrability. And there's this one that I want to kind of employ here, which is to say that in quantum integrable many-body systems, there is an extensive number of constant charges. And that's what I'm going to stick with in this talk. So what I mean by that is that in integrable systems, quantum integrable systems, you're going to have not only these physical charges, for example, the energy or the momentum, but also on top of this, you have all these tower of constant charges, which happen to be also constant in the system. So this looks like quite a miraculous kind of situation, which might make you wonder if it makes sense at all to think about even these kind of models, because that seems very unlikely to happen. But as already Bruno kind of alluded to already, it does happen a lot in one dimension that the model of interest is integrable. So for example, this sine-Grondel model could appear in many different places. One notable kind of situation is where when you look at some low energy effective description of some gaplet systems, where the sine-Grondel model becomes that kind of effective kind of description of a gapless system. In other situations, this kind of model could also appear. So, even if you look at just this model, there is a good reason. There are many good reasons to study the sine-Grondel model. But of course, this is not the only integrable system out there, but you can also consider many other integrable systems, for example, the Heisenberg chain. as Bruno talked about, and also another kind of system called the deep linear model, which I will focus on in this talk. And all these models have their own kind of interesting aspects and use, and also they're realizable in actual experimental setups as well. So I just wanted to emphasize that there are many good reasons to study integrable models, and in particular the dynamics of integrable systems, which might be a bit counterintuitive to what you think. All right. And just to clarify and contrast, I also just put one representative non-integrable model, which is 5-4 theory, whose Lagrangian is given like that. I guess many of you are more familiar with this kind of non-integrable system. And indeed, they would constitute the majority of the physically, sensible kind of many-body systems. And in these models, you have only a handful of constant charges, for example, the energy. And if the model is continuously in space, as opposed to like spin chains, then you also have this momentum conservation law. So yeah, but these are the kind of pretty much all the kind of charges one can have in non-integrable systems. You might sometimes also have a U1 conservation law, but yeah, certainly not more than these. Okay, so this is the kind of contrast between these two models. And how the question I want to pose here is, how does it manifest itself in the dynamics? There's kind of, it's a very different kind of manifestations, but one notable one is the lack of thermalization in integrable systems. What do I mean by that? Well, in non-integrable systems, a kind of conventional wisdom is that from whatever initial conditions, your system is going to eventually relax to some stationary state described by a stationary measure called Gibbs ensemble. So this must be very familiar to you. Whereas this is not quite the case in integrable models because of the presence of these charges. So what you have instead is that eventually the system is going to relax to a stationary state called generalized Gibbs ensemble, or in short, GGE, where the exponential has not only just the Hamiltonian, but all these charges in here. Of course, depending on the choice of initial conditions, it could be that the eventual stationary state happens not to have all these charges participating in this exponential, but in principle, all these charges have an equal right to be there. Okay, so that's the kind of one consequence of having so many charges in the system in integrable models. Okay, so that's the kind of situation that I'd be curious about here. So that's the kind of focus in this talk. Right. So let me be a bit more precise about the question I want to ask, which is about the dynamics. So what I'm interested in here is to ask the following question. So given a many-body initial state, which I denote by this sign, how could I quantitatively characterize its time evolution? And of course, the answer is to solve this very simple, Schrödinger equation, right? The many-body Schrödinger equation, which can be formally solved in this way. But of course, it's easier to be said than done. I mean, in practice, it is almost always impossible to write down an explicit time-evolved many-body wave function like that in integrable systems, and even in integrable systems where the structure tends to be a bit, more structured, you cannot still get that kind of time-evolved wave function. But I want to do something about it, although this seems very formidable. And the reason why I'm curious about that kind of question is because the dynamics of integral systems has been known to be really interesting. I mean, I mentioned this lack of thermalization earlier, and indeed, that was the first kind of thing that people noticed about the dynamics of integral systems. So there is this very famous example, an experiment, which Bruno already kind of briefly introduced in the morning. So this is, so the experiment is like this. So it's called quantum Newton's cradle. So this is depicting the kind of usual classical Newton's cradle. It's a kind of very common desktop toy, if you like. So what is happening here is, I guess I don't have to explain, but just to be complete. So these metal beads are hanging here like that. And what you do is just pull one end of it, one end of the chain of the beads like that, and then you release. And what happens is that it's going to, of course, hit another bead next to that, and then the momentum will be transferred across all the way from the chain of beads, and eventually, the farthest one would go fly like that, and then it will come back like that, and then this kind of motion of beads would persist for a while. And of course, that's not going to last forever because it's usually put on a desk surrounded by an air or something. So there'd be a source of dissipation, and it will come to halt at some point. But people wanted to do something analogous to that using some quantum setup. So what did people do? So what people do is to first confine a gas of particle atoms, particularly rubidium atoms, in a quasi one-dimension potential, which you can sort of create these days, thanks to very advanced experimental techniques, and also because they are now kept at a very low temperature, so you can really have a very precise control over their location, etc. And now, what people then did is to sort of inject initial momentum to this gas of particles by kicking the system, essentially, or sort of providing some pulse called Bragg pulse to the gas of particles, which would impart this gas of particles into two separate gases of particles, and they would just go with like that in the confined potential, and then they would come back eventually because there is this kind of harmonic potential which is trapping the system. So these gas of particles go like that, and then come back, interact, go through, and come back, and in this kind of motion, which pretty much resembles the classical Newton's cradle would also take place in this quantum setup. Okay. And what people observed is that this kind of motion of atoms would persist over very, very many periods of time within the experimentally accessible time scale. And this was quite striking. And so people asked why this was happening at all. But people quickly realized that this can be basically attributed to the fact that when atoms are kind of loaded like this in a quasi one-dimensional setup, they can be effectively described by a very famous integrable model called Lieb-Liniger model, which is integrable. So people quickly realized that there is this underlying integrability, which gives rise to this kind of persistent motion of gas of particles. People observed this kind of pattern, and which very much intrigued people, and I would say triggered this whole, kind of surge of interests in the study of dynamics of integrable systems, which has lasted to this day. Right, but this experiment was done like 20 years ago, almost 20 years ago, but it took people for another 10 years to actually realize that there's a way to characterize this kind of dynamics, inhomogeneous dynamics, using a certain kind of formalism. I mean, this cannot be really described using for example, solving this Schrödinger equation. That's completely hopeless. So people were wondering about the kind of effective description of this kind of dynamics, right? But people didn't quite know what to do until 2016, when our papers basically provided the first recipe to describe the dynamics of this kind of integrable particles. So we wanted to provide a formalism to describe to give you this quantitative description of inhomogeneous dynamics in integrable systems, and that's exactly what we did in the paper that we got this Frontier of Science Award. Okay, so that's the kind of background. So what was the formalism about? So that formalism was heavily based on the concept of hydrodynamics, emergent hydrodynamics. So the idea is as follows. Of course, if you want to faithfully describe the dynamics of these integrable particles, like I have been repeating, you've got to solve this Schrödinger equation. But the idea is that let's just forget about that. That's too ambitious. So what one can do instead is to ask the following question. Is there any circumstance where the degrees of freedom you have to keep track of somehow reduces? And that sounds like a very special situation, but actually it does happen when the system is kind of gently varying in space. In that kind of situation, by saying gently varying, I'm saying that it compares to the microspace length scale, like the atomic length scale, for example. And in that kind of situation, you can say that that kind of system, that slowly varying system, is described by only slow modes, namely constant charges. So you can now reduce the kind of degrees of freedom you have to keep track of to a single kind of degree of freedom, which is the energy conservation law, or the conservation law associated to other charges. And then the question is, when would the system be gently moving? Well, the general expectation is that when the space and time, spatial and time scales are kind of taken very large, one can usually expect that the system is kind of gently varying from whatever initial conditions. So essentially, what we are going to do is to focus on that very particular space and time scale, and claim that in that on that kind of time length scale or time scale, which we call hydrodynamic scale, we can apply this hydrodynamics essentially. So, for example, if you start with this kind of initial condition in a spin chain, just for simplest, I'm taking spin chain, although I will deal with continuum models in the rest of my talk, but just for the acceleration. And suppose the initial condition is like that, just spin up, and the rest is all spin down. Okay. From this initial condition, if you apply this Hamiltonian, or the time of evolution operator e to minus th, that kind of time evolution is going to generate really lots of very much complicated states, a superposition of these states, and of course you cannot quite keep track of all these states. So instead of doing that, you just assume that on this hydrodynamic scale, the only relevant degrees of freedom is the energy, and from that you kind of write down this kind of equation, which is nothing but the heat equation. So schematically, there is a huge reduction of degrees of freedom from this Schrödinger equation to just one simple differential equation, which of course you know how to solve. So this is the kind of power and universality of this hydrodynamic idea, which I'm going to employ in this talk. And because in this model, I'm assuming that this is non-integrable, so there's no other charge. So that's why the energy is only diffusing in the system, but in principle, there could be other charges. But this is just a very simple situation. Okay. All right. So this is the kind of setup. I hope this is clear. Okay. Now, let me do a bit of mathematics. Well, like not exactly mathematics, but I have been avoiding equations. So, but just to lay down the foundation of what I want to talk about, to say. So suppose you have a many-body system, just for generality, with n constant charges. Well, in integrable systems, as you know already, we have only a handful of charges, but in integrable systems, this can be infinity, or at least, extensive, really large. All right. So in that case, you can have these microscopic continuity equations for every charge. So this is just a microscopic equation, which I hope you're already familiar with. And now what I'm saying is that at a hydrodynamic scale, something similar actually holds. So let me now be precise about the scale I'm going to take. So this is the scale I'm going to focus on is what I call the Euler scale. So the Euler scale means that you simultaneously scale both spatial and time coordinates like that by some parameter small l, and you send L to infinity. So this is the scale that I'm going to focus on, and it's often called Euler scale. Okay, and this is done for the charge density, and this average is denoted by like this. And of course, this initial condition. So this average has to be taken with respect to not a thermal state or some stationary state, because otherwise this is just trivially a constant number. Okay, okay. Sorry about this. Oops. Okay. Now, yes. So okay. Why is that? Yeah. So I was talking about this Euler scale average for the charge, but you can also do the same thing for the currents. Okay. So I'm just saying that I'm declaring that I'm going to focus on this particular scaling, which I call Euler scale. Okay. And now for this kind of quantity, both charge density average and the current average, you can write down a so-called Euler equations. So the Euler equations are like this. So this is pretty much similar to that microscopic equation, but this is no longer microscopic kind of equation. It is a macroscopic equation because I take this scaling explicitly here, right? For this kind of scaling, I have this Euler equation. And this is not the microscopic derivation. This is what I expect to have in at least in integrable systems and also in general. So long as you have this non-trivial current here. So in the previous case, actually, in non-integrable spin chain, you do not have such a non-trivial flux for the current, and that is why you have this kind of second derivative term as the leading kind of contribution. But here I expect that there is a generic current here, so that's why I have to focus on the Euler scale instead of the diffuse scale, as in the previous slide. Okay, so this current term is now a functional. Right. So, yeah. So what do I mean by that? So in non-integrable systems, as I said, you have only 2 or 3 charges, or could be even 1. And for these quantities, you can write down hydrodynamic equations like that. So, but I'm assuming that for generality, these 3 charges are not conserved in non-integrable systems. So the first conserved charge is the particle number, the second one is the energy, and the third one is the momentum. Okay. For these 3 charges, you can write down these equations. First one is usually called the continuity equation. The second one is often called Euler equation. Okay. Where this curly P on the right hand side is something called the pressure term. Okay. And finally, the third term is related to the energy conservation. So the second one, which is called the Euler equation, it corresponds to the momentum conservation. So if there's no spatial translation symmetry in the system, like in the spin chain, there's no equation. Okay? But considering a case where there is spatial translations. So we have these three charge equations, and now the only thing you have to know is how to write down this pressure term in terms of the charge density and the velocity. Okay? And this is also called equation of state sometimes. And this is the only microscopic information you have to feed into equations. And once you have it, then your business, you can solve these equations and plot the density profile, etc. Right? And one kind of noticeable aspect of this equation is that generically for any initial conditions, these profiles which develops some very sharp structure called shocks like that. So from this kind of bump, you eventually have this kind of very sharp structure, sometimes called gradient catastrophe. And this is not good. And once that happens, the validity of the oil hydrodynamics stops. But yeah, in integral systems, actually this does not happen. So that is something. All right, so far it's been about hydrodynamics. I hope it's clear. I mean, it's questions. Okay. So now I move on to integral systems. That's what I care about in this talk. But I thought it would be nice to give you a bit of flavor about how particles are trapped, especially how particles are trapped in integral systems. Because this is going to be also important for creation of dynamic framework. So let's start with a very simple case, just one particle. You have one causal particle traveling in space freely with this momentum k1. So of course this momentum and the energy, and the wave function is of course just this simple plane. Okay, I will explain what I mean by this simple. Now, in the two particle case, you have somewhat more material interaction. You have these two incoming particles, and then they now be after some collision or interaction, they travel with different moment. Okay, and by writing like this, drawing like this, I don't mean that they. This is a signal. Then they just. Okay. But still, there has to be moment conservation, total momentum, and total energy has to be constant. Okay, so with that in mind, this asymptotic wave function, assuming that x1 is 2 and assuming that k1 is greater than k2, you actually have this wave function has to have this very simple. What happens is that either the particles momentum is changed, or they just do not. And this is not the way and only the possible combination of these particles. This is the simple function, and this kind of implies that if you just focus on two particles, that it's cannot quite distinguish whether the particle is dynamics is described by integral and dynamics. So you have to look at three particles. Okay, so now we have three particles, like incoming momentum like that and outgoing momentum. But you have still only two conditions that have to be satisfied: total momentum, total energy to be constant. So because you now have only two constraints, there is something new happening here. So this asymptotic moment wave function now not only have this simple superposition of these plane waves, but momenta are kind of permitted. You can have also this kind of extra term, which tells you that the set of momenta doesn't have to be a permutation of the set of incoming momenta. They can take arbitrary values so long as these two conditions are satisfied. Conservation of total momentum and energy. Okay. So this is generic what happens in non-integrable systems, and this second term is telling is characterizing so-called inelastic scatterings. This actually does not happen in integrable systems. So this is the kind of key consequence, one important consequence of the underlying integrability. So there is no inelastic scattering. The only kind of possible arrangement of these momenta are the permutations. So this is very important. And this also implies that these two diagrams describing different kinds of scattering processes are basically the same. So this is, in a sense, the famous Yang-Baxter equation. So this absence of inelastic scattering is really the kind of important aspect that should be really highlighted. Okay, so this is the what happens in integrable systems. So let's now just to make things concrete, I will focus on the model called Lippel-Niger model as my example. So the Hamiltonian is given like that, where the interaction is encoded in these contact interactions. Okay, and this is written in terms of the first quantization form that also write that in terms of the bosonic fields, where you'd have the four-body interactions. Okay, and why do I care about this model? It's because it appears in many places, and also as I kind of briefly mentioned, this Lippel-Niger model can effectively describe the motion of Udar-Cold atoms. So, for example, it is this also appeared in Bruno's talk, but these days, the Lippel-Niger model. I mean, prepare this atoms, atom chip, the motion of particles in these tubes. So this is physically relevant. Now, because you have a number of positive charges which are in involution, you can have this basis that diagonalizes these charges, the quasi-particle basis. So these P1 and Pn are called quasi-momenta. And here HILP is the so-called one particle eigenvalue. Its label I is labeled in these charges. Okay, so this is the basis. And now if you impose the periodic boundary conditions, that would amount to the quantization of quasi-momenta. And if there's no interaction, of course, this pi is just be given by 2 pi times the integer divided by n, which is learned in the first mechanics course probably. However, that's not what happens. Because of this non-trivial interaction, this time you have this additional part, which is phase. Okay? And for the Lippel-Niger model, it's given. So this is an important change coming from interactions. Okay, this is called the bed equation. But now I want to take this thermodynamic limit, sending L to infinity, sending particle number also to infinity, but keeping the equation finite. Then actually this bed equation boils down to the so-called TVA equation. Let's get into detail, which is important. The bottom line here is that you can define so-called administrative states, and it's defined that. And then this guy is now satisfying this integral equation. So, here, this right-hand side is driven by the source term 1 over 2 pi, and this psi here, so phi here is a differential starting funnel, which takes this very simple form, and then finally this rho p is something. So in integral system, we have usually at least two expressions, particle expressions, whole expressions. And that is why you have to, so you have to, in order to get this state, you have to take a sum of the particles and these things. Okay? So this is just a definition. And here NLP is something called filling equation. and define. Here, the epsilon is called pseudo energy, and it's going to satisfy this. Anyway, is important. Make here is that in terms of these sort of TBA quantities, they can really describe the important thermodynamic quantities, for example, green energy, entropy, sometimes called Yang entropy, and most importantly, this GG average of these charges. Okay, now this charge average, so this average taken with respect to some GGP, and it's given like that, where you have to just multiply this density of particles times this eigenvalue, non-particle eigenvalue of this charge in question, and then takes the integral over this quasi. Okay, and this is just a charge, so it's extensive in this system size. If you look at this density of the charge, then you just have this, and it's divided by L, and you're going to get this, which is going to be one important thing in writing down the Hydrodynamic equation. Okay, so this is already one piece that is needed in the Hydrodynamics, but this has been actually known quite. So, but this new addition, which is this, how to write down this GG average of the couplets in terms of these TBA quantities, was the really new input. So, and this is sometimes also called the equation state, and it's given that. The only difference between this expression and the previous expression is that there is this additional factor in the integral called vector velocity, like that. And yeah, basically realizing that it has to be like this, and it's taking this form was one very important technical result in this. And this effective velocity is satisfying another kind of integral equation. All right. And now you might wonder what to make of this. How is there any interpretation? And indeed, actually, there is a nice interpretation to get this. You don't actually even have to know something. So how do I interpret this? Does this come about? There is this kinetic interpretation of velocity. So the idea here is that at a large hydrodynamic scale, all these quasi-particles are actually behaving like solids, meaning that these quasi-particles come like this, and then the only thing that happens when they collide is that they have this phase shift. This phase shift is precisely given by the self-differential differentials. Kernel, which linear model is like that, and then they just carry on. So they go initially, if you focus on this particle, this they push backward, they just okay. So they are behaving like solitons essentially. And this is very important, and this leads to effective velocity as follows. So the effective velocity is essentially the kind of average is the velocity of the quasi-particles when they are traveling distance. Okay, so in the absence of interaction, there's no scattering. So of course, during time t, you're gonna propagate with this fixed velocity v. So the traverse distance is always the product of these, which I do not the traverse distance. But in the presence of interactions, of course that is not the case. The particle you're looking at is constantly kicked by other class of particles. For example, if it's kicked from the right, then it's going to be pushed back. I mean, now I'm assuming that this phi is positive, right? In the linear model. I mean, this is actually not always the case. It could be negative, but for the linear model, it's positive, so it's pushed back. It's jumping. Okay? So when it's hit by another quasi particle from the right, it's going to be pushed. Whereas if it's hit from the left, then it's going to be pushed by the center. So I have to calculate and keep track of all these contributions throughout that piece. And if you just enumerate all these, right, then you can get the total net distance that is quasi-particle. Okay, and you just have to divide by two. And this is actually precisely giving us to this. So this is the kind of nice kinetic picture of vector velocity. So let me just to reiterate, at a hydrodynamic scale, what you can say is that these quasi particles are like solidons. Okay, microscopically not quite true, but large distances that is the case. And then by just focusing on how it's going to kick other particles, you end up with this. So no CBA, no complicated steps, just this picture is going to give you this. Let's find it. So with this, you can write down this equation that, and now this is, so you know, first slice, and now I've just plugged, okay. This one, just we know for many, many years. It's another one, which we discovered in our paper. We just plug these two functions, okay? So functions in here, in the Euler hydro equation, and then you find out this. And because this has to be true for every charge given by I, you conclude that the inside of this component has to be this. That's why you can change the function as it is. Okay. So this is the equation that you get. I mean, now it's nice that there's no I. It's expensive extra label B. This is um, uh, this has the function specific charge. Okay. So that's nice, and you can also write down this J equation in terms of so-called normal mode. I mean, normal mode is actually not a unique object. There are many choices. However, one natural choice is the filling function. And in terms of filling function, this equation can be recast into this one, which is having this nice convective. And this is actually useful for practical purposes as well. And also it's nice to write like this because now one can appreciate is that this GHD equation actually satisfies a very important property called linear degeneracy, meaning that the effective velocity of the particle, quasi particle, does not depend on its own density. So this is always zero when P in both moment quasi moment are the same. So this is kind of interesting, and that's not usually the case in non-integrable systems. But intuitively, this is kind of clear that this has to be the case in integral systems, because remember, according to this kinetic picture, the only way for this quasi particle to change the trajectory, the velocity, is to be influenced by others, kicked by other quasi particles, meaning that its own trajectory does not influence its own velocity. So that is why there is this so-called linear degeneracy, and this also implies that there is no shock in systems, meaning that from whatever initial conditions, the profile of the density is not going to develop any shock structure. And this is very obvious and visible consequence. Okay, and this actually also has an important consequence, which I'm not going to talk about. Anyway, so that's the start. So let me so let me talk about one particular initial function problem, which called bifunctional function. So just prepare two subsystems. But initially, summarized with respect to different temperatures. So this is going to give you this kind of initial condition in terms of rate, right? And then you know that the solution is going to be given because both initial condition and the dynamics itself are invariant under the scaling spatial. So this is going to be, the solution is going to be just a function of this rate psi, like that. And in terms of that, you can calculate the energy current of this junction in the equilibrium steady state. Okay? This is current, and it's always. So let me tell you how to do some limiting situations. So the first situation is simple. So you take this particular limit called Tonks-Girardot limit. So remember this lambda was the coupling constant. This is a very strongly interacting limit, but because of some structure model, this actually forces the system to be effectively because you can see that this phase shift is actually becoming zero, making that effective function in the system, and as a result, this effective velocity is basically the same as group velocity. That case, you can solve this very simply, and this is okay. So the energy current in the non-equilibrium steady state is just by this expression, and this is there's this persistent current which quickly drops as it but this is kind of trivial, so let me focus on a bit more trivial limit. So this is the limit where you keep temperature very low, so it's low temperature limit, under which the model is effectively described by so-called Takato, which is just the form of field theory with C. Okay, so in that case, you have this kind of solution essentially, and you can just use this solution and which actually takes a very simple form. So it just tells you that there's just a kind of constant current in between the light form, and then also the light form changes. That's the kind of interesting aspect of this nest current in quantum field theories in general. And also interestingly, this can be compared with another kind of exact result, which was already known before. So for any generic CFTs, you can have this do the same partial protocol and ask the energy covering of the interface if x equals 0. And it's been known rigorously that it has to take this form and where this in the numerator you have this central charge, and if you by taking c equals 1, yes, this exactly produces this result which you just obtained from solving GHD function. So this is very much consistent because, as I said, at this low temperature limit, the Lippinger model is potential liquid, which is equals 1 C2. So all consistent. Okay, so that is quite solid, right? Okay, now a bit of experiments. I mean, okay, actually, this the both are really stop, but let's let me see if you again. So there have been a fair number of experiments out for verifying the validity of GHD. The first one was that was to use this atom chart to use particles confined in one dimension, and but they to start double potential, this kind of function, and you release so it's branching from this. Okay, so that's what they did, and as you can see, the agreement is very satisfying. It's noisy curves from data and solid curves. So with GHD equation, and they are really but what is really more important conceptually here is that this really verified that GHD has to be used in describing the dynamics of these particles, and conventional dynamics doesn't quite reproduce the right results. So by conventional dynamics, explain to you, I mean that even for the linear model, you can just forget about all these higher concept charges and try to solve
these equations only. I mean, in the Lippinger model, these charges are still conserved, so you can pretend that these charges, conserved charges are absent and try to solve these equations consistently. You can do it. And indeed, people did it. And this actually has been also, had been routinely done in theory papers. People knew that it's not kind of correct, but anyway, people didn't know how to do other than solving these equations. So people have been doing it. And in some situations, this conventional hydrodynamics does give rise to a qualitatively accurate results, which are agreement with experiments. But this experiment showed you really clarified the or invalidate the use of conventional hydrodynamics. It is for this kind of problem. So if you start out with this double wave potential, you see these dotted lines are really heavy GHD or experiment. Right? These kind of short functions. So this is not quite good, and yeah, we have this GHD. The GHD surfaces. People also measured the rapidity distribution. Sorry, is the particles through the so-called time of flight plot. Because if you trap initially and try to expand these particles freely in 3D, then you can sort of read off the momentum after that kind of quench, and from that you can infer the rapidity distribution. So because you cannot quite directly observe the distribution experiment, so you have to observe moment from each distribution. Anyway, so people have done some checks of the validity of the GHD, and all have been very nice. All right, so time. So okay, let me say a bit more about the recent developments, which were not discussed in the original paper. So the first one is that actually GHD allows you to calculate so-called transport coefficients. So for example, this kind of outsider matrix, it's just a function where the so-called root weight is subtracted is actually calculable within the framework GHD. And why is it interesting to study this kind of things? It's because this is going to tell you how easily current is flowing in the system. For example, if you start out with this kind of density initial density profile in integrable systems, what happens is that this will split into two parts. Moment of conservation will okay, and we're talking about linear model. Spinches. Or actually spinches. Anyway, so what happens anyway is that this initial problem is split, and then they would sort of propagate ballistically space, ballistically meaning that they propagate at velocity and it's scale. Okay. Now, what happens on top of this is that each of these bumps is now going to diffuse in space, meaning that their profile is broad in space. But the rate at which it happens is slow. This is the propagation bumps. So the root of t and the rate at which it happens, I here is going to be given by the oscillator. And D here is actually rated to Osaka matrix by this so-called Einstein relation. And this is going to be, this then allows you to write the Navier-Stokes equation for the integrable systems. So this is the Navier-Stokes equation for the integrable models. But in fact, this is actually not entirely correct away from the linear response regime. So if your initial condition is within the linear response regime, then this is effectively true. But in general, if your initial condition is not very close to some equilibrium state, then generically there would be some long-range correlations developing. Dynamics giving rise to corrections to the dynamics. so setting another way, if you keep a full non-linearity, or if you're forced to keep non-linearity because of conditions, then you have to have some additional. And so generically, Navier-Stokes equation, that is in its known form, is not valid in integrable systems. Navier-Stokes equation is not valid in integrable systems. Which, yeah. Yes. Yeah. Completely different. I tried to make these different. I'm using different fonts, but yes. Yes, the Drude weight is actually telling you about this ballistic information. So you've got to solve this unless you have no flux system. And Drude weight can be also indeed computed. So techniques of mobility and yeah, it's quite satisfying in the system because both of these can be computed exactly using speed, which is usually not possible. You cannot determine transport coefficients exactly in systems unless you so this is nice. So this could probably make you wonder if there's something happening, so there's something strange happening in diffusive systems. Indeed, it is completely different in the following sense. In fact, in integrable systems, there is no normal diffusion. And this is quite unique situation, because typically normal diffusion comes about because of slow modes being kicked by some fast modes that are writing down equations. These fast modes are usually kind of arranged in the white nodes. You write down in fluctuating, and they would sort of contribute to constant kick these slow modes, energy, charge, densities. But that is not the case in integrable systems. There's no fast modes to start with. So there's no normal diffusion. Then you would ask, where does the diffusion come from in integrable systems? In fact, diffusion in integrable systems come from entirely the initial conditions. And this is quite interesting. So this kind of diffusion is something we call convective diffusion. And this is the main source of systems. So what do I mean by that? So when you start your dynamics, usually prepare some answer. Okay, maybe local equilibrium or maybe something by function explaining, and they have some fluctuations. And what happens is that in integrable systems, the fluctuations in the initial condition are very much stably propagated by the ballistic propagating laws. So these diffusive fluctuations at the diffusive order in the initial condition are also propagated by the same equation that would propagate the average points. And then show fluctuations will be propagated according to the order equation, and then giving rise to the kind of diffusive behavior you observe at finite time. So this is really different from the non-integrable case, and we realized this only recently. So you can see that these works talk about this kind of stuff pretty. Okay, so this is what is happening in integrable systems: fluctuations only from the initial condition, no dynamic general fluctuations. So this is and also the property that I mentioned of linear degeneracy actually also implies that there's no super diffusion in the system, at least no super diffusion prescribed by so-called non-fluctuating hydrodynamics would happen in the system. So generic kind of mechanism, super diffusion has been known, but that is not going to happen in the systems. However, there is an exception. For example, if you look at the spin current in the isotropic Heisenberg model, then it's been known that this spin, it's basically super diffuse. And this has been a great mystery in the community, which I think is still open question. And but it has to be coming from internally. So I guess time to talk about what was put in the title and the fluctuations. I just wanted to say that fluctuations can be described by also using kind of extension of the hydrodynamics concepts. So just JHD has been very successful theory of describing dynamics systems. It has also fields, physics, math, quantum dynamics, etc. And also it has predicted interesting physical phenomena. So it's not just beautiful formalism, but also it has new things to further investigate. So I have explained what I've been doing, and with the Windows talk, you probably have some idea about this thing now. But
Okay, thank you for the nice talk. So, is there any question?
So thank you for the interesting talk. In your outlook, you mentioned counting statistics.
yes,
And that seems to me quite related to the quantities I computed.
yes,
Which, I mean, we were only able to do the calculations using a semi-classical approximation.
Yeah.
And so it seems that you believe you can do it exactly.
if asking, and that's precisely what I wanted to talk about, but had to skip briefly. So there is a method called macroscopic fluctuation. So it's a kind of tool established in physics community. So it's basically a path integral like formalism. So what you have to do is that you write down some kind of path integral. For in this case, it's focusing on this kind of. This is just a generating function. This j hat is the time integrated function, and I want to calculate this equilibrium. And this is and when you calculate, you have to do is to take path integral of the density. So these density fields, we have a big one, energy density, energy. But now you're seeing that the energy field is a fluctuation, not just a fluctuation. And then you just make sure that this describes this initial fluctuation properly. And then you propagate your energy fluctuation. So you're seeing that energy fluctuation, not just energies, but also energy fluctuations is satisfied by. So this is a kind of hydrodynamic approach to general.
So this average would be the analog to the correlation function of the tunneling operator.
Well, I mean, if you want the correlation functions, for example, you can just hit this by lambda, right? Take a derivative with respect to lambda, and then that's going to generate a bunch of current correlation functions.
But I mean, what I needed for computing tunneling is the correlation function of bosonic exponents. So I really need the full thing.
Yeah, you can do that. Right? I mean, you can also calculate this average of each of them. And then parameter of if you take derivative of alpha, you're going to generate a function.
So I really want the correlation function of bosonic
Exponent, like
e to the I phi at time t with e to the I phi at time 0, and it seems that the full thing which you're writing down here.
Yeah, I think you can do that. I believe you can do that, provided that the t is sort of like very large.
Yeah.
So there has to be some large one, but I believe you can.
Would it then be different from the semi-classical?
That I wouldn't know, but in principle, this can keep track of all kind of.
Yeah,
There's
and
no
the
Yes.
finite solid with things.
Say again.
A finite solidum with finite width of.
Maybe
multiple
I have
particles.
to look into that, but yes, I
Okay, it
it
sounds
says it.
exciting.
Yes.
Okay.
Yeah, this stands for the scaled cumulative. It's just this.
Okay. Any other questions? If there's no any other question, let's thank the speaker again.